Okay, good morning, everyone. I will try to make the same way that Jorge did last week. No, I will try to present some of the work that we did in the past year. So I will start with this work. You still see my PDF, no, Jorge?
Yes.
Yeah. Okay. So
Yes, we say.
Okay, good. So the first work that I would like to present is this modeling broadband browser emission with convolutional neural network. So this is a new method that we just was developed here in collaboration with some people. So the main idea behind this that when you have some observed data from browser observations and you want to make the modeling of the observed data with the traditional methods. Traditional method, I mean, when you have these numerical codes and you take into account everything, so the injection, cooling, etc. of the particles. So these are computationally very heavy. So whenever you try to model this observed data with these numerical codes, technically this is very problematic because it takes very long time and you could wait tens of days, and this is not good. And if you want to make a very deep study, you need to have something that is working much faster. So the method that we propose is based on using the neural networks, because these are becoming very efficient tool in all the field of the science, including astrophysics. So this is why we apply these neural networks to model the emission from blazars. So what we did, we selected for our model, in this case is a self-synchrotron Compton. So you have the electrons that they are injected inside the jet, they are under the magnetic field interacting via synchrotron emission and self-synchrotron Compton. So the same electrons are upscattering the synchrotron photons. So for this model, we consider the large range of the parameters. So all the model parameters are in this table and the corresponding range. Then for this range of parameters, we split in a narrow range for all the considered parameters, and we generated the spectrum using the code that was developed here in Armenia, Soprano. So using the Soprano, we generated like 200,000 spectrum for different values of the parameters. Then we use these convolutional neural networks. So the idea was that we want to train on this generated data. So the networks will understand what is the relation between the input, which is in our case the model parameters, with the output, that is the spectrum. So apparently it works very well. So when you train these neural networks, then you are able, so this is the general flow, how it works. So you generate parameters, you split by different train, test, validation, and you train your convolutional neural networks. So as soon as we train, we understood for the different state of the parameters in very different range, the network is actually very accurately representing the reality, which is the spectrum. No. So as soon as you train these neural networks, then you are done, because before, when the numerical codes, it used to run like a day or several days. Now within a minute you can perform the modeling of your data. So this is what we demonstrated here. So we took these two, one of them is this very well-known blazar, which is Markarian 421, with this very rich data set, and you see that we were really able to very quickly model this observed data. So we introduced it so that this model can be applied on various sources. So the example is presented here. So with this blazar here, and sorry, okay, just okay. And this modeling is important because it gives you the values, and you can also investigate the correlation between different model parameters, etc. So this everything that I'm presenting here was not possible to do before with these numerical codes, because it was quite heavy to run. But now it's very fast, and within minutes you can perform the fit of as many data as you want. So we extended this study not only for the case of self-synchrotron Compton, but also for the more complicated scenarios. And this includes this already when you have this external Compton models. So it means that you don't have only the photons that are produced inside the jet, but you have the photons that are coming from the external to the jet. So this makes the things more complicated, because now you need to consider the cooling of the electrons in a more dense, in the medium, which contains more photons, so the cooling is more stronger. So you need to take into account all of these processes. So the corresponding neural network, this case, is more difficult than in the previous time, because you have more processes, and your kinetic equations, these times are more difficult to solve. So, but anyway, the networks, again, we consider the broad range of the parameters. Now the model parameters are more than the before. So you have like, before you had the 7, now you have 11. And still the performance of in this case, we generated 1 million of data, and still the performance of the model was quite good. What I want to mention here, that in order to generate this data, we were very collaborating with some company in USA, private company, which they were building some tools to compute very long computation, and they were happy to test in our case. So they used this computation. So instead of like waiting 1 month for the computation, it took like 17 hours to make this computation. Strong server in the Amazon, and this was done all by this private company, and they were happy to pay also for these servers, and they were testing their system. So at the end, when we built this neural network, in this case again, we were able to nicely reproduce all the ACDs, and we used to model the observed data. Just to demonstrate why this modeling is important, that you don't do it. If you look the global minimum and you don't look the local minimum, this is just, you can see in this plot that we see one of these objects, there is this bimodal distribution. So it means that there are two sets of the parameters that equally well models the data. So this is nice, because it means that there are two different conditions that your model is explaining the data, so it gives allows more deeper investigation of the object. So these works are currently ongoing, so that the third paper will become out, so it will allow also to not only the model the photon spectrum, also the neutrino one, which is very complicated, because here you take into account also the hadronic interactions. We are just right now working on it, and I think very soon the third part and the fourth part of this project will come out also. So when we developed these tools, we understood that it would be nice so that it would be accessible to everyone. And there was some project that we were working for a very long time. It was this to build a data center. And we were able to build this. Data center here in Armenia. So the name is Markran Multivalent Data Center, and this is the corresponding paper in Astronomical Journal, which explains the technical details and provides the information about this. It was accepted publication a few months ago. So the idea of this data center, that it contains data for all the type of blazars, which are continuously analyzed here, and it is easily accessible to everyone. And we don't provide only the data from the catalogs that like other data centers do, but we are analyzing so many data here. Just to demonstrate that, here is an example. For example, in the gamma ray band, if you access any of the catalogs or any other data center, you can get the data, which is the red one over here. But the data that we analyze here in Econet, so you see that this is time solved data, so you can get the data from different periods, and this is way much more that it contains in any of the available catalog. So this is why this contains a lot of data and allows the users to just download this data that they can study. So this is the structure of this data center. So there are two main functionalities. The first one is data part, which you can really access, download, use data of these different bands, archival data, optical, X-ray, gamma ray data, and most of these data are really new and they are just analyzed here. And there is this web interface, which is very easy for everyone to use. So you just type the name of the object that you are interested in, it goes to our system, brings back you the data, and this is the entire data that you can see that you get. And this is visualized in a very novel way. So this is like interactive. So you can just play with these accesses that you have here. You can change the unit, make a filter, etc. So we provide also the possibility of the users to work with the data. And this is not only about the data access, but this is the entire data that you can download for the different objects, and you see that it's very rich in all different bands. Not only you can access the data, but you also can perform the fit for you. So this is an example of a fit done with the SEC model. Another example, you can do that. I'm sorry, just handiplan and and there is the modeling with the external inverse compound model, and this is everyone can use it. So after this data center was online, I think it was very actively used. So this here you can see the, let's say, the user community of our data center, and all the correlate countries have everyday users, and they are downloading data, they are making the feed. So you see this includes
incredible, fantastic.
All the European countries, it's the USA, Russia, China. I mean, we have the users. Every month there is like between 350, 400 people that they are using this data center. So this is becoming really very, very active, and I think in the community is very well received, because the amount of the data, the way that we provide the fitting, etc., it's very active, and I'm very happy that the people really appreciate. And I mean, we have like countries which are investing a lot of money to build data centers, but instead of using their own data center, they are using our data center here. I think this gives a lot of value of this data center which we have here. And I hope the uncolored countries will increase also in time, but right now we have really from everywhere active users, which I think it's very good. Okay, so there are other works that I would like to mention. So another work that
this is so very, very impressive. I hope everybody can look at this map and work toward its expansion. But I think this activity developed at ICRANET Armenia is very, very impressive. Keep going.
Thank you, Professor. So I just to mention a couple of other works. So this first one, which was done in collaboration with Paolo Giomi, which is, I think, it's very interesting result, because we understood that, we know that the blazars have this very complicated spectrum that goes from radio to high or very high energy gamma ray band, but we find out that if you measure the spectrum in a very narrow, which is in a microwave band, using this NeoWise data, it contains so much information that there is a correlation that allows you to predict where the peak and where the intensity should be of the synchrotron component. So it means that for the future, when you need to make the multi-wavelength observation, you don't need to have the entire spectrum to get a feeling where the peak should be. So only the measuring the data at microwave band, the slope allows you to make this kind of prediction. So we found that this relation that we present here is quite enough to predict where the peak of your synchrotron component should be. And this is very important, because when you know the peak of the synchrotron component, the flux plus the luminosity, then it's very you can make some extrapolation in the very high energy gamma ray band to understand whether these new instruments like CTA or etc., they can make some observation and how many blazars they can look in the future. So we made some kind of estimates, and we showed that there will be hundreds of the objects in the sky that the CTA already can observe. And this is very important result, because when they are building this instrument, they need to have some number of the estimates, which kind of blazars and which level they can see. And these estimates, I think, is very well received in this very high energy gamma ray community, and they are referring this to estimate the possible numbers that possible sources that CTA will be able to observe in the future. Here are some values we predict with the probability. So, and we show how many objects in total blazars CTA can observe. Another work that I would like to mention is this study of the distant blazars. So we selected all the gamma ray emitting blazars which are in the very distant, so in high redshift from 2 to 2.5, because in 2 years ago we studied all the blazars that they are above 2.5. Now we cover the range of from 2 to 2.5. So in total there are 79 objects that they are observed emitting in the gamma ray band in this distant. So we did multi-wavelength study of these objects. We try to understand how the different emission in different bands correlates for these objects in X-ray, optical, gamma ray. We looked at the variability, and what is interesting, some of them, since they are very distant, and some of them are flaring, and you see that this luminosity over here is 10 to 49 erg per second. So it means that sometimes they are very, very bright and very powerful objects in the sky. Not only we looked how the multi-wavelength emission changes in X-ray or in the gamma ray band, so we made this theoretical modeling of this observed spectrum for all of these sources, and we try to understand how these parameters are connected, how they change depending on the distance, etc., etc. And I think this is very important, because if we want to understand how these blazars are evolving in cosmological distance, we need to know their physical properties. We need to understand what is the connection between the jet and different distance, and to understand how it evolves in time. So these are some works that I want to highlight, but there are of course much more which I don't have time and I don't explain them. So some of them are done within the MAGIC collaboration. These are about the observation of different blazars, some of famous ones. So there are some of the galactic objects, but what I would like to mention about MAGIC, in total we have like 15 articles published in last year. So, but what I would like to highlight about this MAGIC observation is that the young researchers from here are visiting La Palma, and they stay there for 1 month to take part in these shifts, the observations, which is very good, because not only they learn how to work with this data, but they understand also how to use these two big 17-meter telescopes. And I think this is some knowledge that maybe in the future can be used somewhere else, because if the people they follow of these big telescopes, how to get the data, how to use them, etc. I'm sure that in some days this will be very helpful for us as well. And we are continuing this to be inside the collaboration. This year also we'll send some 2-3 young researchers to La Palma. And of course there are some other works also we do with the collaboration with Paolo Giomi in Abu Dhabi, etc. But I don't think that I need to mention them, because the main activity that I showed is what is just happening here. And if you have some questions, I will be happy to answer.
You have still a lot of time. We have time for discussion.
Yeah, and we can discuss.
Please don't forget to send a 10 lines summary to the chairman of the scientific committee, who is collecting all of them put in the proceedings of this meeting. 10 lines with the author, co-author, and summarize the key point. I mean, maybe indicate this beautiful picture, or add some other one, and we will create, and indicate also in the 10 lines the part of your documents which are contained in the 3 volume. In these 10 lines, you should indicate and send them to the chairman of the committee the link to the audio presentation in the 3 volumes, indicating the key points. Okay?
Okay, I will do it.
This is essential.
Sure, I will do it.
Okay. And there are maybe the chairperson can ask if there are questions.
Narek, can you hear me?
Massimo,
Yes.
I can, but not. I mean, it seems like you are speaking from very far. So if you could speak near the computer.
Use my computer because there is the echo. Wait a minute.
Massimo, sorry, I cannot hear you.
Now better.
Now better.
Okay, yes, look, I clearly understand that the tools that you have developed is, let's say, is making an easy access to the data. I'm wondering what is the advantage for the modeling of the data? That maybe is something more complicated. Can you expand a bit this issue?
Yeah, okay. Yes, for the modeling, actually, so this neural network that we built, so this is our in, let's say, in the back end of the system. So there are the model that we considered is the search synchrotron compton for a very broad range of parameters, and external compton with very broad range of parameters and models that we included. No, so basically, this is the main difference that we have with the other, let's say, such tools that they are making the modeling. So if you try to model any of the data that is available in the community, how they do is that you need to find some initial description of your data, and then you have to make this Markov Monte Carlo chain around these data points that you find. So the problem of this approach is that if you find some initial description of your data and you make the Markov chain Monte Carlo, you are looking for the local minimum. No one says that this is a global minimum, and you don't know if the parameters that we are obtaining is the true statistically better ones. No, instead, the method that we develop, since it's based on these neural networks, we are not looking any initial distribution. So we just plug the data. We know the model, so we know the framework. So this is an ACC or external compton, and we are looking all the possible parameter. All the possible parameter ranges, and then the likelihood is trying to find the parameters that they are best describing your data. So in other words, we are trying to find the global minimum. So we know all the parameter space, and we are trying to find the global minimum in the likelihood surface. So this is why when you try to make this fitting, or you are trying to make this modeling, you get some understanding of the parameters that are statistically better representing modeling your data. I mean, just to give you a feeling, these kind of studies are so active in the Blazar field, because when we put our paper on arXiv, was like after 3 or 4 days, the same study was done by this. You remember there was this person from the GRB community in Blazar, Mastikiadis, Maria Petrapolo, etc. They did exactly the same work that we were doing, but they were later than because we were first to make this kind of study. So this is the modeling that we are using here. The behind is all based in these neural networks. So this is why it becomes very quick. And just to mention, now we are modifying everything. So we are implementing also these large language model possibilities, like all this ChatGPT, etc. that you have. So I think in 1 or 2 months there will be the possibility that the users can just go there and ask it like a question. Can you download this data? Can you make a modeling? You will have some assistant that help you to make the fitting, the modeling. And this tool also is quite new with this possibility of to perform not only to explain the scientific literature, but plus to make some actions like to get data, to make the fit, or etc. These works are currently in progress. I think in 1 month or 2 will be finished, and this will be quite new as well.
Okay, Narek, thanks for your first question, but now I have a first answer. So I have another question.
Sure.
Can you imagine to develop this kind of machine learning approach for a database different from Blazar, like supernovae, nova, or gamma ray burst? So to extend all this kind of analysis to all other transients, that would be very important.
Thanks, Massimo. I think this is a very nice question, comment. To be honest, my idea is something like this: to build something, the beginning that will be for Blazars, because I know them and I can show that we are able to do these things. But the next steps, we will really expand this to supernova, to GRB, or etc. Of course, collaborating with the experts in the corresponding field. So just we wanted to start from the small scale, that is Blazars, then to expand to include other transients, etc., etc. So I was having some conversation a week ago to try to make the things for TDS also, these digital distribution events, or etc. Because now people are getting really some nice interest of this machine learning stuff that it could be very nice. So there was some guy who was really very interested to apply this machine learning stuff for the TDES, etc. But of course, for Supernova or GRBs, this will be nice as well. And our future direction is to implement these transients as well. We want to start to have something stable for blazars, get an expertise of how these things works, then to move other objects, other group of other type of objects as well.
Yes, I think if I make a suggestion, maybe we could start with a database on classical novae. They probably are less interesting than others, but the database of novae is smaller,
Yeah.
and we can see what is coming out from that, and then we can expand it toward gamma reburst and supernovae.
I completely agree with you. I think this will be very nice. I think when next time we meet, we can also discuss this thing, because now we have this expertise that we are able to build not only the data, as you mentioned, for the supernova or whatever, no, plus we are able to extract all the scientific literature, to put in some special vector space and build a large language model that will help us, so the people to understand better the things. No, so if we try to combine these two things, it will be very nice application of this machine learning stuff that is very fast developing with the classical data from astronomy and astrophysics. And I think this will be the future that will be really very helpful for everyone.
Okay. There are a good perspective on this. Thank you, Narek.
Thanks, Massimo. And of course, we can discuss with you how to progress and which direction.
Yes, of course.